In this lecture, we want to introduce the acid-base properties of salt solutions. I want to remind you that a salt is not just sodium chloride, it's any ionic compound. So we're going to look at the acid-base properties of ionic compounds when they dissolve in water. Recall the equilibrium established when the weak acid, acetic acid, is dissolved in water. Acetic acid donates an H plus to water, forming a hydronium ion and acetate ion. This is an equilibrium. Most of the acid remains in this form because it's a weak acid, but there's some acetate ion produced in solution. And we, of course, remember that acetic acid is the acid and acetate ion is its conjugate base. We also recall that the Ka expression for acetic acid can be written like this, and that the Ka is 1.8 times 10 to the minus 5. It truly is a weak acid. Now let's do a thought experiment, and let's imagine that you have this solution in your beaker, but you're going to selectively take some tweezers and pick out all of the acetate ions from this equilibrium, and then you're going to plunge them directly into pure water. And when that happens, the acetate ion can showcase its ability to act as a base. Again, this is a thought experiment. We take the acetate ion out of this equilibrium and we plunge it into water, just pure water, and we find this equilibrium set up where the acetate ion will abstract an H plus from water and reform a little bit of acetic acid and some hydroxide. Again, this is an equilibrium situation. If we write a Kb expression for acetate acting as a base, it would look like this. The product of the concentrations of the products divided by the concentration of the reactants at equilibrium, and we see that this Kb value is quite small. So acetate is acting as a very weak base, but a base nonetheless. So what are some things to note here? The acetate ion, which remember is the conjugate base of the weak acid acetic acid, can undergo hydrolysis, meaning reaction with water, to form a basic solution. And that's just what we showed here. Acetate ion undergoing hydrolysis, reaction with water, to form a basic solution to produce some hydroxides. The Ka of the acetic acid times the Kb expression for the acetate acting as a base turns out to be equal to 1 times 10 to the minus 14, and this is called the Kw, which we've discussed before. We can prove this by taking the Ka expression of acetic acid right up here and multiplying it by the Kb expression for the acetate right here. If we do that, you can see that the acetic acid concentrations cancel out, the acetate ion concentrations cancel out, and what's left is an expression that says the hydronium ion concentration times the hydroxide equals the Kw, or 1 times 10 to the minus 14, which you already knew. But what we're trying to point out here is that the Ka of acetic acid times the Kb of its conjugate base, acetate, equals Kw, or 1 times 10 to the minus 14. So I write this right here as an abbreviated expression. This is in general true for any conjugate acid-base pair. Now also here, if we take minus the log of the Ka value, which remember is called the pKa, times minus the log of the Kb value, which would be pKb, that will be equal to minus the log of the Kw. So we have here 4.74, the pKa of acetic acid, 9.25, the pKb of the acetate ion equals 14, which is the pKw. And I've written this over here. So the pKa plus the pKb equals the pKw. There's a lot of letters to say in that sentence. If you note here that 4.74 plus 9.25 doesn't exactly equal 14, that's not uncommon. That's just due to some rounding errors in the determination of these Ka and Kb values. The thing to remember here is the Ka of a weak acid times the Kb of its conjugate base equals Kw, and the pKa of the weak acid plus the pKb of the weak base, its conjugate base, equals pKw, which is equal to 14. Let's do an example problem. Let's suppose I ask you to calculate the pH of a solution made by dissolving 2.48 grams of sodium acetate in enough water to make 100 milliliters of solution. Just to remind you, the formula for acetate ion can also be written as C2H3O2-. First of all, what we want to do as we approach this is simply calculate the initial molar concentration of the sodium acetate. And that's easy to do. We take 2.48 grams, divide by its molar mass, and then divide that result by the volume of solution in liters to get 0.302 molar. You want to recall that sodium acetate, which is an ionic compound, will completely dissociate in water to the limit of its solubility. Considering the fact that the solubility of sodium acetate is around 120 grams per 100 milliliters of water, it's ridiculously soluble in water. It appears that solubility is not a problem here. So I'm going to write this expression. You take solid sodium acetate in water and you get sodium ions and acetate ions. Now recall from the previous slide we did that thought experiment where we actually took molecular tweezers and picked out all the acetate ions and threw them into pure water. Well, of course you can't do that. So the only way you can get a sample of acetate ions is in a compound that pairs it with an ion that won't interfere. And in this case, when this dissolves, you'd get 0.302 molar sodium ion and 0.302 molar acetate because it completely dissolves. And what we're just going to tell you here is that the sodium ion is not going to interfere. We're just going to state that it's neutral in water, and we'll talk more about this later. But the point is, we've found a way to put acetate kind of by itself just into pure water. And of course, it's not by itself. There's sodium ions around. But since the sodium ions are neutral, there's no acid-base chemistry going on there, so we can safely ignore them and concentrate on the acetate ion, which is basic in water. Here it is undergoing this hydrolysis reaction. And what we're going to do here is literally calculate the pH that results from this equilibrium by setting up an ice table. We start out with 0.302 molar acetate and no acetic acid and effectively no hydroxide. Fill in the change row, the equilibrium row. We now are going to check on whether or not we can assume X is small in our calculation. If we take the initial concentration of the acetate and divide by the Kb value, we see we get a ridiculously large number, which of course is way bigger than 400. So we can surely skip the quadratic here. So when we write out the Kb expression for the acetate, it would be x squared over 0.302 minus x, or x squared over 0.302, assuming x is small, and we set it equal to the Kb value for acetate, which we stated on a previous slide. If you solve for x, which is the hydroxide ion concentration, you get 1.3 times 10 to the minus 5 molar. The POH is then 4.89. The pH is then 9.11. Note here, you have to remember that X is the hydroxide ion concentration. So sometimes folks make the mistake here of just saying, well, the pH is minus the log of this. That's actually the pOH. So we have to determine the pH from that. Bottom line, this is basic in water. The pH is greater than 7. And just as a point of interest, we can calculate our, quote, percent ionization, which in this case is just reflects the extent of reaction to the right. And you can see that most of the acetate stays in this form. It doesn't undergo hydrolysis, but enough of it does to form a basic solution. Now, before we proceed, let's pause for a minute and take a closer look at the actual hydrolysis reaction of the acetate ion once again. So here we have it here, just rewritten from a previous slide. And what we'd like to do here is just ask some questions about this hydrolysis reaction. The first is, why would acetate ion abstract an H plus from water to form hydroxide and acetic acid? Why would it do that in the first place? Even if it doesn't do it to any great extent, why does it do it at all? Does the formation of acetic acid over here make you do a double take? Because we're thinking, well, the hydrolysis reaction produces a basic solution, but we're producing as one of the products acetic acid. So why isn't the solution acidic? And finally, why doesn't the acetic acid that forms just immediately react with the hydroxide that's being formed? Let's look at these questions one at a time. The first is, why would acetate ion be interested in abstracting an H plus from water? Well, recall the acetic acid ionization. If you put acetic acid in water, it does ionize slightly, but the favored form, remember it has a choice of two forms, the acid form or the conjugate base form. If you put acetic acid in water, it seems to favor the unionized acid form. So that would mean that if we independently put acetate ion into water, for example, in the form of solid sodium acetate, the acetate ion will attempt to abstract H plus ions from water to form at least some of the preferred form, which is acetic acid. Well, does the formation of acetic acid in this hydrolysis reaction, even though not a lot is formed, but does the formation of it mean that the solution should be acidic? And the best response I can come up to for that question is that acetic acid acts as an acid when it ionizes and donates an H plus. The acetic acid here on the right side is in the unionized form, so in a sense it's not acting as an acid because it's in its unionized form. And wouldn't acetic acid that's formed just react with any hydroxide that's formed? And the answer to that is yes. The acetic acid and hydroxide form can react and go back to the acetate in water. But remember, this is an equilibrium situation. The rate of the forward reaction is equal to the rate of the reverse reaction. The equilibrium does favor the left side because Kb is quite small, but at any given time, a small amount of acetic acid can and does coexist with hydroxide. This small amount of hydroxide is what makes the solution slightly basic. So we've illustrated so far that the conjugate base of a weak acid, remember which was acetate, the conjugate base of the weak acid, acetic acid, undergoes hydrolysis in water to produce hydroxide and form a basic solution. And we can say this in general terms. The conjugate base of any weak acid undergoes hydrolysis in water to produce hydroxide and form a basic solution. Weaker acids have stronger conjugate bases. Stronger acids have weaker conjugate bases. And this is simply the result of the fact that the Ka of the acid times the Kb of its conjugate base has to equal Kw, this number here. So if the Ka goes up, meaning the acid gets stronger, the Kb of its conjugate base has to go down. Its conjugate base gets weaker in order for the product of these two to always equal Kw. Now we actually introduced this concept in slides number 10 to 11 of lecture 1, only we just didn't use this equation quite as explicitly. So let's look at some representative examples here. And I want you to note once again here in a table that we're going to build that as the Ka of the acids decrease, the Kb of each corresponding conjugate base increases. So let's look at several weak acids and their conjugate bases. Here's chlorous acid. It's one of the stronger weak acids. Its Ka value is 10 to the minus 2. Its conjugate base would be the chlorite ion. The Kb value of this is quite small. If you make up a solution that's 0.302 molar in sodium chlorite, remember we can't just take the chlorite, find it somewhere and plunge it into water. We have to have it paired with something, and we decided sodium ion was a good thing to pair it with because sodium ion is a spectator here. If we do that, we get a pH value of around 7.7, so it's slightly basic, which makes sense. This would be a really weak base. Let's go to a weaker acid, nitrous acid. Ka is smaller. That means the Kb of its conjugate base nitrate is going to be larger than the chlorite. And we'll keep all the solution concentrations the same so that our comparisons are fair. And if we make a 0.302 molar solution of sodium nitrite, delivering nitrite ions, we get a little higher pH, 8.31, because the weaker acid has the stronger conjugate base. If we keep making the acids weaker, we've now come to acetic acid and acetate. We now get a pH of 9.11 for the hydrolysis of acetate. And if we go to an even weaker acid like hypochlorous acid, its conjugate base is the hypochlorite ion, and a 0.302 molar of solution of sodium hypochlorite is pretty basic, 10.5. So you see as the acid strength is decreasing, the conjugate base strength is increasing. Acid strength decreasing, conjugate base strength increasing. Now the conjugate bases of really strong acids, such as chloride from HCl or bromide from HBr, nitrate from nitric acid, or perchlorate from perchloric acid, have no significant effect on the pH of a solution and are considered neutral in water. Let's see if we can illustrate this. Suppose we dissolve sodium chloride in water, so we have sodium ions and chloride ions. We've said that we'd talk about this later, but sodium ions are neutral in water, and let's look at chloride ions in water, and let's write a hydrolysis reaction, chloride plus water forming HCl and hydroxide. You'll notice I have X's through this arrow, meaning this does not happen to any appreciable extent. Well, why? Well, chloride has no motivation to abstract an H plus from water to form HCl and hydroxide. This is because one of the products, if it did that, would be the strong acid HCl, which by definition cannot exist in water in the unionized form to any significant degree. So chemists would call chloride a pathetically weak base, which we did mention in a previous lecture. It's very poor at trying to abstract an H plus from water, and effectively it does not, and so chloride, the conjugate base of the strong acid HCl, is neutral in water. So we expect a solution of sodium chloride to be neutral. Now, in a manner analogous to weak acids and their conjugate bases, we can talk about weak bases and their conjugate acids. So we say the conjugate acid of a weak base undergoes hydrolysis in water to produce, this time, hydronium ions and form an acidic solution. At this point, this may start to sound a little confusing, but just follow along here. Let's look at a weak base. Recall the equilibrium established when the weak base ammonia is dissolved in water. We have ammonia undergoing reaction with water to a slight extent to form ammonium ions and hydroxide. Of course, ammonia is the base. The ammonium ion is its conjugate acid. Now let's suppose we separately dissolved ammonium ion into water, and we can do that by making a solution of ammonium chloride. Well, why is that? Well, remember, chloride is neutral in solution. So if we put ammonium chloride in water, effectively what we're doing is just putting ammonium ion in water, because chloride is neutral. So let's calculate the pH of a solution made by dissolving 1.615 grams of ammonium chloride in enough water to make 100 milliliters of solution. If we calculate the initial molar concentration of ammonium chloride using its molar mass, you'll probably not be surprised to find out that it's a 0.302 molar solution. What we're trying to do here is compare apples to apples, so we're keeping our solutions at the same concentrations. If we dissolve the ammonium chloride solid in water, we get ammonium ions and chloride ions, 0.302 molar of each. We said chloride ions are neutral. The ammonium ion we claim is going to be acidic in water, so let's write a hydrolysis reaction, and you can see that the H plus from ammonium ion could be donated to water to form a hydronium ion, leaving ammonia on the other side. This is an equilibrium situation, so we're going to calculate the concentration of hydronium ion at equilibrium. So we set this up and we say, since this is an acidic situation, we look at the Ka of the ammonium ion, ammonia times hydronium ion over ammonium ion concentrations, and we're going to assume here that X is small. Well, why can we do that? Well, the Ka value here is so small that it's pretty much a slam dunk that we can assume X is small. Now you might ask, where did this Ka value come from? Because I'm not sure you're going to find it on a table that's accessible in your textbook or on the lecture slides necessarily. So let's find out how we got the Ka of the ammonium ion. Well, recall that the Ka of an acid times the Kb of its conjugate base has to equal Kw, 1 times 10 to the minus 14, at least at 25 degrees C. So here the Ka of the ammonium ion times the Kb of ammonia has to equal 1 times 10 to the minus 14. If we solve for the Ka, that means we take the Kw and divide by the Kb, and we can look up the Kb in a table because we can find the Kb of ammonia. So we can calculate the Ka of the ammonium ion even though we can't look it up in a table. When we do that and solve for X, we get a number that looks familiar, but this time this is the hydronium ion concentration, so the pH is 4.89. So a solution of the ammonium ion in water does produce an acidic solution because it undergoes hydrolysis with water to produce its conjugate base, here ammonia, but more importantly, hydronium ions. So we say ammonium ion, which is a conjugate acid of the weak base ammonia, does indeed undergo hydrolysis in water to form an acidic solution. Well, in an analogous manner to weak acids, the weak weaker bases have stronger conjugate acids, and stronger bases have weaker conjugate acids. Again, this is simply the result of the fact that Ka of the conjugate acid times Kb of the base has to equal Kw. So if the base gets weaker, if Kb goes down, Ka would have to go up. Weaker bases have stronger conjugate acids. And again, we introduced this concept way back in lecture 1. Now here's some representative examples. We're going to build a table here like we did for the weak acids, and we're going to try to show as the Kb of the bases increase, the Ka of each corresponding conjugate acid decreases. So we're going to start with a very weak base, aniline, pretty small Kb value. Its conjugate acid would be the aniline ion. Remembering the name of that is not a big deal. The big deal here is seeing that this is the conjugate acid of aniline because it has an extra H plus that's missing from the aniline. Well, what would be the calculated pH of a 0.302 molar solution of aniline chloride? Notice here again, we can't just get a bottle of aniline ion off the shelf. We need it paired with something that will not interfere in our little experiment. Chloride is neutral, so this is a source of this ion. And we find that this is fairly acidic, pH of 2.56. If we make the base stronger, we find that the conjugate acid is weaker, and the calculated pH of a 0.302 molar solution of pyridinium chloride is now 4.66. Still acidic, not quite as acidic. Let's make the base even stronger, which means its conjugate acid is even weaker. This is the example problem we just did, and a 0.302 molar solution of ammonium chloride is 4.89. And finally, methylamine, which is the strongest base on the list, would have the weakest conjugate acid, and we calculate the pH of the methylammonium ion in water to be 5.58. Still acidic, but certainly less acidic. So we see as the base gets stronger and stronger, the conjugate acid strength gets weaker and weaker. So let's try to make a summary of the calculated pH values of the aqueous solutions of the various salts that we've discussed so far. And remember, all the solutions have the same concentration, just to keep things fair. If we take sodium hypochlorite and put it in water, the important reaction is that the hypochlorite ion undergoes hydrolysis to form some hydroxide, and we calculated a pH of 10.5. Sodium acetate, the acetate ion undergoing hydrolysis, gives us a pH of 9.11. Sodium nitrite, a pH of 8.31. Sodium chlorite, a pH of 7.72. Notice in all of these, the paired ion here is sodium ion, which is neutral, and a spectator ion, and so it's just not included in the equilibria, which are showing the hydrolysis of these conjugate bases. Sodium chloride, of course, is neutral in water, and so the pH of that should be 7. Now we're going to start dissolving some chloride salts. The cation here is the conjugate acid of a weak base, so it undergoes hydrolysis in water to form an acidic solution. And these are the ones we just covered on the previous slide. So we can see that as the conjugate acids become stronger, the pH is dropping. And we go all the way down with aniline chloride to a pH of 2.56. And remember here, Chloride is the conjugate base of the strong acid HCl, so it's considered neutral in water, and therefore it's just a spectator ion here, and so it's not included in the equilibria. What I want you to appreciate here is the fact that just simple ionic compounds can have their own acid-base chemistry and solution, and the acid-base chemistry is all over the map. Some solutions could be basic, some solutions could be less basic, some solutions of ionic salts could be neutral, and some could be acidic. In part 2 of this lecture, we want to start talking about metal ions and whether or not they can ever show acid or base properties, and we'll look at some other examples.